Meanwhile, the current starts out as max and it kind of dips down like that exponentially. But because of this time constant, because of this opposition to the flow of voltage, what happens is it displaces voltage and current throughout the circuit. But across the capacitor, that displacement, no matter what value the resistor is, or the capacitance value, microfarads or picofarads or whatever, you still have a 90-degree displacement between voltage and current. If you put a scope across it, that's exactly what you would see. It doesn't, like I said, it doesn't matter what these other component values are, or whether this is a 25 microfarad or 100 microfarad capacitor. It's still always going to be, it's going to be out of phase by 90 degrees. So if you look at if we put a scope across here, what you'd see is, you'd see a displacement like this. So you have from here, this point to this point, is 90 degrees. So current starts out right away. We use current as a reference for a capacitive circuit, and mainly for a circuit that's dominated by capacitance. And the voltage would start 90 degrees later. And that's the way you'd see it. Like I said, it doesn't matter what the other values are. It's always going to be that. Across the resistor, they're going to be in phase. So you'll have voltage and you'll have current basically occurring in phase. And then the combination of the two components, based on whether it's more reactive or it's more resistive, there's going to be a phase displacement from what the source is. So if we put a scope out here, if this was, let's say that each component dropped 10 volts across it, that the X of C was equal to 50 ohms, and R was equal to 50 ohms, then we'd have a 45-degree displacement between voltage and current. And the reason for that is the vector relationship, the phase relationship. So if we set up a plane like this, the Cartesian plane, resistance is on this axis, and these are called J operators, they're part of a complex number system. So down this axis is X of C, and up this axis, the positive side is X of L. Resistor is just a straight line. So we normally work within this quadrant out here. So if you were to look at a capacitor value, let's say the capacitor here was 50 ohms, and the resistor was 50 ohms. So you have something that looks like this. This is called projection modeling. So you have a vector that's this way. That's X of C. Resistor, this is from here to here, is R, and then you have a displacement from here to here, which is Z. This is the impedance. So you have a Pythagorean triangle. So you have X of C on the opposite side, resistance is on the adjacent side, and the hypotenuse is the impedance. And if these are balanced, if this is 50 ohms, this is 50 ohms, that means the magnitudes are exactly the same, the lengths. So you have something in here that's, would be 45 degrees. From here to here is another 45 degrees. So it's 90 altogether for that right triangle.
Is the impedance going to always be on the hypotenuse?
Yeah, it's always related this way. They're also related with voltage as well. This is equal to Vs. This is Vc. So it's a Vs or Vc, and then this would be Vc. This would be Vr. So you can also relate it to voltages as well. They're proportionally the same, voltage and impedance. Vs would be related to impedance. Xc would be related to the voltage across the capacitor, and of course the resistance would be related to the voltage across the resistor. But the maximum angle you can get, if you were mostly reactive, it would be 90 degrees. And that's what I was saying before, you always have the 90-degree phase shift across the capacitor. If you have a little bit of resistance in there, it's gonna be something less than that, less than 90. You know, and if it's mostly resistive, it's gonna be 0 degrees, you know, or a resistive circuit. You know? But because of this displacement, you know, we can have some odd voltages out here. Like in this case here, this is actually an example from the book, the CET book, where they give you the two voltages, and then they ask you what the source is. And ordinarily, we would just use Kirchhoff's law and just add this stuff up, but because of the phase relationships between the voltage and current, we have to, between the two voltages, we have to add them vectorially. We have to do this Pythagorean.
Could you just do that example?
Yeah, yeah. So what we do is we plug this in right here. Use this formula. So you have Vx.
You gotta have you. Three magic cards.
Vs would be equal to 70.7 volts. Okay. So that would be the answer. You know, if you take the square root of the two, then you square it and then take the square root, you end up with the source voltage. You know? I'm sorry, this is 7.
Well, we.
7.07.
Those last.
But there's a few of these on the test. They do it with inductors too. It's exactly the same thing. You know, if they give you two values like this, you know, just plug them into this formula. You know, like I said, you got to add them vectorially. You have to use the square root formula for the Pythagorean theorem.
But they have to give you those values, right?
Yeah, they'll give you these values, and this, you know, I mean, don't be thrown by it. It's, you know, it's pretty simple. You know, you got the other two components on the sides. You got resistance, the voltage across the resistor, and you got the voltage across the capacitor. Now, so all you need to do now is find out what the hypothesis is.
Why am I missing something?
So what is it, 10 volts across each component?
Yeah.
And then the source voltage is 7 point.
I'm not
Yeah.
seeing 7.07.
Yeah, how would you can't increase the voltage across resistors.